Okay, good morning, everyone. I'm back for another session of calculus. Let me quickly summarize the ideas that we went through in the first tutorial. We talked about differentiation being a rate of change. But let me back up. We talked about calculus being calculus consisting of two main branches, differentiation and integration, and that they reverse each other, the processes reverse each other. We talked about the different ways in which you can look at differentiation. You can look at differentiation as the rate of change of one variable with respect to another. We can think about differentiation as giving rise to a gradient function. And we can think of differentiation as being the reverse process of integration. In this tutorial, I'm going to take a look at differentiation as a gradient function. So, without further ado, let's go. Differentiation as a gradient function, or let me be a little more specific. I want a color, man. I have a color ready. Jeez. Still trying to learn to use this thing properly. dy dx as a gradient function. If we were to compare, here's a line, and I'm going to give it an equation, standard equation. Let's say y is equal to mx plus c. And if I were to ask you, well, specifically y is equal to, let's say 2x plus 3. And I were to ask you what's the gradient of that line, you will tell me 2. If I were to be more specific and ask you to tell me what the gradient of the line is right there, you'll tell me 2. And right there, you'll tell me 2. And there, and there, and there, and there. You would keep telling me 2. The moral of that story is the gradient of a line is the same at every point along the line. Okay. Now let's compare that with a curve. Here is a curve. And I'm not going to give it a specific equation. I'll just call it y is equal to some f of x. And I would ask you, what's the gradient of the curve here? Well, you may not know, but that's okay for the purposes of this discussion. And I would ask you, what's the gradient of the curve there? Again, you might not know, but at least what you will be able to tell me is that the gradient is different at those 2 points. How about on top there? It's different there as well, and there, and there, and everywhere else. The moral of this story is that the gradient of a curve changes at every point along the curve. So let's make that our first important point. Gradient of a curve. That's the first important point. The second important point is the gradient of a curve can be obtained from the gradient function, dy dx. In fact, that's one of the reasons you call it a gradient function. And the third important point is this. If I were to draw a tangent line to the curve at a point, right there, tangent is a line that just touches the curve at that point. Let me draw another tangent there. Let me draw another tangent here and so on. You can clearly see the gradient or the slope of those tangent lines change as you go along the length of the curve. And in fact, there's a direct relationship between the gradient of a tangent to a curve at a point and the gradient of the curve itself. They're actually equal. So that's your third important point. The gradient of a curve at any point is equivalent to the gradient of the tangent to the curve at that point. Okay, so here's a first pretty straightforward example. Find the gradient of the curve y is equal to 7x cubed plus 3x squared minus 2x plus 1. Find the gradient of that curve at the point where x is equal to 1. So if we needed the gradient of the curve at the point where x is equal to 1, the first thing we need to find would be the gradient function dy dx. Now, the last tutorial taught us how to differentiate polynomial functions. So at this point, we should be okay with that. Dy dx, the gradient function, is equal to 3 7s 21x squared plus 236x. The minus, the one that comes down, 1 by 2 is 2. It should be a minus. Minus 2. And again, whenever you differentiate a constant, this guy at the end there, you get 0. And we should remember why. Constant is fixed. Constant doesn't change. Differentiation measures rate of change. And therefore, the derivative of a constant would give you 0. All right, so this is the gradient function. Notice the gradient function depends upon the variable x. Everywhere inside that expression, you have the variable x. So if I want the gradient of the curve at the point where x is equal to 1, I simply substitute x equal 1 into the gradient function. So when x is equal to 1, dy dx is equal to 21 times 1 squared plus 6 times 1 minus 2. How's my arithmetic here? 21 and 6 is 27 minus 2, that's 25. That number, 25, is the gradient of the curve at the point where x is equal to 1 that same number also represents the gradient of the tangent at the same point. Alright, kind of straightforward. Let's try another one. Same instructions. Find the gradient of the curve. Let me look at my notes here. Example number 2. Find the gradient of the curve y is equal to 4 upon x at the point where y is equal to 2. As I change this one up on you a little bit, I'm asking for the gradient of the point, and I'm giving you the y coordinate of the point instead. The concept, however, does not change. You will still try to find the gradient function dy dx. So let's at least start with that. Y is equal to 4 upon x. That's not quite in the form of a polynomial. So what we have to do is to use our knowledge of indices and rewrite that as y is equal to 4 times x to the minus 1. Everybody should know that. You throw the x up into the numerator and it becomes x to the minus 1. If you differentiate that, dy dx, you will get minus 1 by 4. That's minus 4 times x. And you subtract 1 from the power, you get minus 2. If you tidy it up a little bit, you get dy dx is equal to minus 4 upon x squared. This is my gradient function. This one might be a little more tricky than the first one, because again, as you can see, the gradient function depends on x. But I didn't give you a value of x. I didn't ask you for the gradient at the point where x has a value. I gave you the gradient. I wanted you to find the gradient of the curve at the point where y has a certain value. Well, that should still be no big deal, because we have the equation relating y and x right there. So because the gradient function requires a value of x to be substituted, then I need to go back up to the gradient function, plug in the y value, and that will allow me to get the corresponding x value, which I would then need to use into the gradient function. So let's try that. When y is equal to 2, we know that y is equal to 4 upon x, and therefore we can say that 2 is equal to 4 upon x. Everybody can do that transposing. That's a little bit of algebra. You should end up with x is equal to 2. So at the point where y is equal to 2, x is also 2. By the way, that just happens to be the case in this example, where both x and y have the same value. So don't go about thinking that that's generally true. And now we can take the x value, x equal to 2, and plug in to the gradient function, dy dx, which is minus 4 upon x squared, becomes minus 4 upon 2 squared, which gives me minus 4 upon 4, or minus 1. The minus 1 is the gradient of the curve. And by the way, at this point, I have both coordinates. For the point, I have both the x and the y coordinate. So this minus 1 is the gradient of the curve at the point where at the point with coordinates coordinates 2, 2. Both x and y end up being 2 in this particular example. Okay, so they don't always have to give you the x coordinate directly. I'll give you one more variation of this. Example number 3. Find the gradient of the curve and go into the curve. Y is equal to x plus 3 times x minus 2 at each point where the curve cuts the x-axis. At each point where the curve cuts the x-axis. Okay? This one is interesting. Clearly, however, because this is a curve and they're asking for the gradient of a curve, the concept still remains the same. You still need to find the gradient function dy dx. So let's at least start with that. That's not in the standard form of a polynomial, so we'll expand out the brackets. Y is equal to x squared. This will give me, looks like minus 2x and plus 3x, so that's plus x. I think I'm right. I'll double check my algebra there. 3x minus 2x is x. And then 3 by minus 2 is minus 6. This function now is in the standard form of a polynomial. I can differentiate. Dy dx is, at this point you should be experts, 2x plus 1. Okay. Notice in this example, they did not give you, or certainly not directly, the x value to plug in, because they want the gradient at each point where the curve cuts the x-axis. So the curve has to cut the x-axis. The curve has to cut the x-axis at some point or some set of points. They didn't give us that. But we should know. We should know from all the work that we've been doing before that whenever a curve cuts the x-axis, y is equal to 0. So they didn't tell us directly what the x-coordinate is. They didn't even tell us directly what the y-coordinate is. We're supposed to know from our previous basic knowledge that whenever a curve cuts the x-axis, y is 0. We should know that. That's how you find your roots and so on, your x-intercepts. So we're going to go there. The curve cuts the x-axis where y is equal to 0. This is standard fare. Y must be 0 whenever a curve cuts the x-axis. So we're going to go back to the equation given. We're going to put y equal to 0. Now we're going to use the factorized form because obviously that gets us to the x values rather quickly. So when y is equal to 0, 0 is equal to x plus 3 times x minus 2. And if you have the product of two brackets giving you 0, that would mean either the first bracket is 0 or the second bracket is 0. Or the second bracket, x minus 2, giving me 0. So it appears as if there are 2 points at which the curve cuts the x-axis. That x is equal to minus 3 and that x is equal to 2. I can even summarize the coordinates of both points. Go back there. Minus 3, 0. That's 1 point at which the curve cuts the x-axis. and 2, 0. That's the second point at which the curve cuts the x-axis. And at each of those points, they're asking us for the gradient. Well, we get the gradient of a curve from the gradient function. You can clearly see that the gradient function depends on x there. So every time you plug in a different value of x, you get the gradient of the curve at that point. So at this point, when x is clearly minus 3, dy dx is equal to 2 times minus 3 plus 1. This gives me a value of minus 5, it looks like. And the other one, here, when x is clearly 2, dy dx is equal to 2 times 2 plus 1. Ooh, that's interesting. And the gradient here, dy dx, is equal to 5. Negative gradient, nothing wrong with having a negative gradient, nothing wrong with having a positive gradient either. So at those two different points, the curve has two different gradients, and you can find the gradient on that curve at any point that you so choose. I'm going to stop this tutorial here, and I'll add in a worksheet later. Might not add in the worksheet. Well, should I? Yeah, why not? It'll be a short worksheet. I'll give you 3 problems on that. Worksheet. Number 1. Find the gradient of the curve y is equal to 1 upon root x at the point where x is equal to 4. Number 2. Find the gradient of the tangent to the curve y is equal to 2x into 3x squared minus 4 at the point where x is equal to 2. And number 3. Find the gradient of the curve and the gradient of the curve y is equal to 3x cubed minus 12x minus 4 at the point where the curve cuts the y-axis. Yeah, that should keep you busy and out of trouble for a little while. Busy and out of trouble. All right, so we're going to call this a wrap for this worksheet. I'm going to immediately do a second worksheet.